Hi, and welcome to Econ 480. These videos were recorded while I taught the class over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. As a result, these videos are going to be shorter than a normal lecture and then may have unnatural transitions. But I hope you enjoy them anyway. Bye now. All right, we're ready to go. So today, this is our third lecture, and we're going to talk about what I call basic inference and endogeneity. So early on, when I sort of like um, designed the order of topics in this class, in my mind, I was just going to talk about um, estimation and inference for sorry, estimation and identification first, and then I was going to do inference in the second part. But then inevitably, we were talking at some point, especially in your homework and sometimes about papers where they'll do some basic t-test and things like that. So even though I'm going to focus on inference in the second part of the class, today I decided that I'm going to review what I'm calling here the basics. Okay. And so today is sort of like we're going to do that without getting into too much detail. And then we're going to start thinking about endogeneity. So last class we continued talking about regression and least squares, and we focused on solving for subvectors of beta and estimating those subvectors, and then we discussed the properties of least squares. In particular, we talk about unbiasedness, the Gauss-Markov theorem, consistency, and asymptotic normality. And when we um, went over asymptotic normality, we saw that the limit invariance was this thing that we call B. Then we talk about how to estimate this B. Today, we're going to use this last result, the asymptotic normality and the estimation of B, to talk about what I call basic principles for inference, or inference 101 if you want. And then we're going to move to linear regression when the expected value of x times u is not 0, which is called endogeneity. Okay. Are there any questions about last class that you still have before we get started? All right. So let's get started. We're going to consider the same model that we've been talking about before. Here, y, x, u is a random vector where x and u are scalars that take values in the real line, and x is a vector of dimension k plus 1. As always, we assume that the first component of x is a constant. So beta is dimension k plus 1, whereas the first beta naught is a constant term, and all the other ones are slope parameters. So far, we have assumed what we call our four basic assumptions. Here's the first one: is expected value of x u is 0. The second one, expected value of x prime is finite. In other words, x has finite second moments. And then the third one, and that there is no perfect collinearity in x, which essentially gave us that this matrix over here is invertible. And then the last one was that the variance of xu is finite. And we needed that because that was the object that appeared in our applications of the central limit theorem. So under these four assumptions, we established asymptotic normality last class of the least squares estimator. And the statement essentially is that it's square root sorry, square root n beta hat n minus beta converges in distribution to a normal with mean 0 and variance b, where b had this so-called sandwich form, where we had the bread here, which is just the expected value of x prime inverse, times the mean, which is expected value of x prime u square, which is essentially this variance over here, and then the bread again. And we discussed how to obtain consistent estimators for this B under two different assumptions, which is first describe and prove the result for the homoscedastic case, and then we wrote at least the expression for the general case or the heteroscedasticity consistent estimator of B, but we didn't prove that it was consistent. We said that we're going to do that later in class. So what we're going to do in the first part of today's class is to develop methods for inference under this additional assumption 5, which is that the expected value of x prime u is non-singular. Okay, and you see that that appears over here. Why do we need this assumption? Well, eventually, as you know, all the tests are gonna take this B inverse. Or if you think about the scalar case, we're gonna be standardizing by the variance or the standard deviation. For that, we need that to be different than zero in the scalar case, or invertible in the matrix case. And for that, we need to make this assumption. Okay. So, um, so as you see, I'm showing how we add layers of assumptions to get the conditions that we need to make applications of the tools that we intend to apply. Okay. All right. Now this is moving fine. Yeah. Okay. Um, this is a background. Consider the following version of what I call here a testing problem. We're going to observe data IID, and I'm going to denote the data here by W. In our case, W is just Y and X. Okay, is has size n, and it comes from distribution P. Okay, if you look here, you see that I parameterize the family of distributions or index distributions by a parameter, in this case beta, and beta belongs to k plus 1. Okay, so um, then in this version of the problem, you want to test a hypothesis about the parameter that index the family of distributions, again, in this case, beta. And then typically you will write a null hypothesis that says beta belongs to some subset of its parameter space versus the alternative that it belongs to the complement. So here, beta naught and beta 1 form a partition of RK plus 1. And, of course, they're both non-empty. So in our context, beta will be the coefficient of a linear regression, and beta naught here could be any partition of RK plus 1. For example, it could be that we make a statement about the entire vector beta is equal to 3 or less than 4, or we make assumptions about linear components like beta 1 is equal to 0 or equal to 7 or greater than or equal to 2, or we make statements that require combinations, say linear or even nonlinear, of different betas. Beta 1 plus beta 2 is equal to 0, or other stuff like that. We'll see some examples as we move forward. In order to do this, we need the so-called a test function. And I want to use this notation, phi n, to denote a test function. And phi n is just going to be a function of the observed data. And a test function returns the probability of rejecting the null hypothesis after observing your data. Okay, so sometimes I noticed in the past that when I write this statement, some students get confused. And the reason is probably because in practice, or at least up until now, most of you have only focused on the so-called non-randomized tests. And non-randomized tests mean that the function phi over here takes only two values. It takes the value 1 for rejection. It takes the value 0 for non-rejection. So it's the probability that is degenerate is 1 or 0. However, a test function may also include tests that are called randomized, and they will take numbers strictly in between 0 and 1. We're actually going to see one of these when we get to the end of this class and we talk about permutations and randomization tests. So at that point, we're going to get back to this discussion. But from here until that particular point, we're just going to focus on this type of tests that are called non-randomized, which are the ones that you're probably most familiar with. So, what is a common case of a non-randomized test? Well, most often, as I wrote here, phi is the indicator function of a certain test statistic. I'm going to denote the test statistic by Tn, the function of the data, is greater than some critical value, Tn 1 minus alpha. Okay, so this function phi is just going to be the indicator that our test statistic exceeds the critical value. So examples of tests that take this form are most of the ones that you already know. A wall test, quasi-likelihood ratio test, Lagrange multipliers, and the like. So the critical value here, Cn, okay, could be deterministic, which is the one that you, again, probably are most familiar with, which is, for example, the quantile of a normally distributed random variable. The 1 minus alpha over 2 quantile of a standard normal, or something like that. But it could also be random, okay? And so it's something that you get, for example, by some form of simulation. including the bootstrap that we're going to talk towards the end of the class. We're also going to talk about, as I said, randomization test, subsampling. All these are resampling methods that gives you a critical value that it happens to be random. That means that every time you run the algorithm, you're going to get a different cutoff. Okay, but we'll cover both of these cases in class today again because I'm trying to do the basic inference stuff. I'm going to focus on the deterministic case, the case in which we're just going to get a fixed number, for example, the quantile of a normal. So then we say that the test is pointwise asymptotically level alpha, or sometimes called consistent in levels, if the limit of the expectation of this test function, which is, in other words, is the limit that of the probability that the test rejects, okay, does not exceed alpha for any beta in the null hypothesis. This sometimes people say under the null hypothesis, the rejection probability does not exceed a tolerance level that we pick, okay, that is usually denoted by alpha. Notice that alpha appears over here. So when you choose alpha, that affects your critical value and it determines the property of your test. So this is not the only notion or concept to say that a test works. You'll see words here like, pointwise is a word here, asymptotically is a word here. So you can imagine that there are tests that could be of level alpha in finite samples, that there could be tests that instead of being pointwise are uniformly valid, and so on. We're not going to talk about any of those distinctions here in 480. I'm just going to focus on this version, which works sufficiently well for the settings that we did in this class. They happen to be inappropriate in other settings, for example, that are relevant in I/O. And so that's why there are other notions that kick in that case. But I talk about that in 481, but we don't have time to do 480. Anyway, so let's start with the simplest case, which is a test of a single linear restriction. So we're going to denote by R, a non-zero k plus one dimensional vector. We're going to let C be a scalar. And then we're going to consider this null hypothesis that says that R primes beta is equal to C. So we're taking a linear combination of the vector beta, and we're saying, well, this particular linear combination is equal to some number that we hypothesize that we're denoting here by C. The alternative hypothesis is that doesn't happen. So that is R prime beta is not equal to C. An important case, probably the most important case, or at least the most popular one, is when R selects the S component of beta, one arbitrary component. And so in that case, this same null reads as beta S is equal to C. Okay? And so you just have a vector of dimension k plus 1. You care about the first loop parameter, say beta 1, and you pick that beta 1, and then you take hypothesis about that beta 1. Now, given the result that we had in the first slide, the continuous mapping theorem implies that square root n r prime beta hat minus r prime beta conversion distribution to a normal with mean 0 and variance r prime b r as n goes to infinity. And since this matrix B, we assume by our assumption 5 that we had it is non-singular, then r prime b r is strictly positive. So in addition, the continuous mapping theorem implies that for whatever consistent estimator we use for B, R prime B hat R conversion probability to R prime B R. Okay, so as long as we have a consistent estimator of B, we also, of course, have a consistent estimator of R prime B hat R. So we need to choose first a test statistic, and I wrote here natural choice of test statistic. This problem is the absolute value of the t statistic, okay? And the t statistic is this guy over here. Square root n times, r prime beta hat n minus the hypothesized value c divided by an estimator of the standard error, okay? So in the notation that I used before, our test statistic is just going to be the absolute value of the t statistic. So capital Tn is the absolute value of t stat. And notice that when R selects a component of beta, say the first component or the second one or whatever, this business R prime B hat, blah, blah, just picks one of the diagonal elements. The diagonal element of B associated with the coefficient that we are testing something about, which is then what you typically use when you do a t-test about the component C being equal to 0. In that case, C is 0. And then here, this guy is just the square root of the diagonal element of this matrix. Okay. And that's what you do. So the next thing is, what's the critical value? This is the test statistic. Notice that if you are wondering why are we using this particular test statistic, I just wrote that this is a natural choice. And as I said, today I'm not going to get into details of these things, but there are essentially two features that you want from a test statistic. The first one is that large values of a test statistic provide evidence against the null hypothesis. And if you say, like, well, why is that? Well, because we have chosen to use a rule that rejects when t is large. So we're just saying we're going to use a test that whenever t is really large, we're going to reject. But whenever t is not that large, we're not going to reject. And so we want a t that has that feature, that large values of t provide evidence against the null hypothesis. So that's the first thing. The second thing is that we want these t statistic to be, in many cases, not all the time, but in many cases, sort of like tractable. By that I mean a test statistic that we can say something about the distribution under the null hypothesis, or at least the limiting distribution under the null hypothesis. And that happens to be the case for these t-stat, as you may know. So what's the critical value? Well, we need to choose the critical value so that the test satisfies the properties that we want, which in this case is consistency in levels. And what I wrote here is that a suitable choice of a critical value is just the 1 minus alpha over 2 quantile of a normal. And so let's see why is the case. So under H naught, we have that the probability, say under beta, that phi is equal to 1. Okay. Is the probability under beta that that statistic is greater than C1 minus alpha over 2. This is again the probability under beta that the absolute value of the test statistic is greater than this value that we pick. And you can write this as the probability that for then R hat B hat minus C is greater than our critical value plus the probability, same guy, less than the negative of this thing. Okay. Now, this converges again under the null hypothesis to 1 minus the CDF of a normal C1 minus alpha over 2 plus CDF of a normal at negative C alpha over 2. And this is equal to 1 minus alpha over 2 plus alpha over 2. And this is alpha. want to clarify something basic here, but just in case, take note. When we say under H naught, we'll replace T with R prime beta so that can apply our asymptotic normality result. Essentially here and here. So this choice of critical value makes sense because by choosing these, we guarantee that the limiting rejection probability of this test does not exceed alpha. Actually, we show something stronger than that. We show that it is equal to alpha. All we needed was that it didn't exceed alpha. Um, so that's how the argument works here. So we have a test that we know how to compute the test statistic, we know how to compute the critical value, and we know that this combination of test statistic and critical value leads to a test that has a property that or the requirement that we were looking for. So are there any questions about this derivation here? Comments? The construction may be modified in a straightforward fashion for testing one-sided hypothesis. Okay, so sometimes you don't want to test it's equal to zero. I know it's equal to C or whatever, it's dominant, but in many contexts, you just want to do one-sided cases. Okay, and so you just change the test statistic instead of using the critical value, the absolute value. Just remove the absolute value. Okay, and then you just reject if the test statistic is greater than the 1 minus alpha quanta. Okay, I'm not going to go through that. I'm assuming that is straightforward. And then also, there's something called the duality between hypothesis testing and the constructions of confidence regions that tells you essentially that if you know how to do hypothesis testing, then you know how to construct a confidence interval or a confidence region. And if you know how to construct a confidence region, then you know how to do hypothesis testing because these are dual problems. In particular, in this case, for example, suppose that we want to construct a confidence region of level alpha, or 1 minus alpha, would you say, for each component, say beta s of beta. Then what is a confidence region? A confidence region can be described as all the values of C such that your test does not reject the hypothesis that beta equals that value. Okay, so if you look at this statement, it just says collect all the values of C that are not rejected by your test. Well, it turns out that in this case, this expression over here can be manipulated and you get to a closed form, which says that this confidence interval is just your least squares estimator minus the critical value you're using times square root n beta hat divided by n. And then the upper bound is just going to be your least squares estimator plus the critical value times square root n beta hat divided by n. And this confidence region, by the properties of the test that we're using, satisfies this requirement over here. Okay. Again, if you ask yourself, what do you want, okay, out of a confidence interval, you will want something like this, which is a limit as n goes to infinity of the probability and the beta, let's say beta s is contained in your confidence interval, is greater than or equal than 1 minus alpha. In case we're getting something stronger, which is that it is exactly 1 minus alpha. Okay. And then once you know, as I said, to test any type of hypothesis, you can always construct a confidence region by the so-called inverting the test. And inverting the test means just do the test for all the values that you can possibly make and then collect all the ones that are not rejected. So that conceptually is very easy to say. Sometimes depending on the setting and if this parameter here is high dimensional and so on, could be complicated to do in practice, but sometimes meaning from a computational point of view, but it's still done in many settings. Okay? And this particular one has the advantage that for a alpha 5%, this guy is typically 196, right? And then people always use this rule like, estimator plus minus twice the standard error, which is exactly what this formula over here is saying. But all this comes from this duality between and construction of confidence intervals. So here you have a graphical illustration of confidence intervals. Okay, this is just for testing the mean, not beta. Okay, we have is here the true parameter is 100. Okay, which is this horizontal line, and then each of these vertical lines is a confidence interval given the data that you have, and then this is supposedly a 95% confidence interval. So what does it mean? Just to clarify, a 95% confidence interval means that if you manage to look at all these possible confidence intervals that you can get with different sample, you're guaranteed that, say, at least 95 of them are going to include the true value, which happens here. All the ones that are black, okay, are include, the horizontal line, but there are a couple of guys, these red ones and the blue ones, that do not include 100, okay? And those are the ones that are fine. Those are the ones that we're saying sometimes you're going to get one uh, that are not going to contain the true parameter, and that's going to happen with probability no higher than 5%. It's an asymptotic statement, so here in a finite sample happens 6%. But, again, because that's an approximation. So, questions? All right, keep going. Test of multiple linear hypothesis restrictions. Now we're going to introduce this matrix R, which is, I mentioned, P times K plus 1. And C is, instead of being a scalar, as before, is a p-dimensional vector. We're going to consider testing the null hypothesis that R beta is equal to C versus the alternative that doesn't happen. And one of the assumptions that we're making here is that the rows of R are linearly independent. Remember, R is a matrix of restrictions that you choose. So all we're saying is that you're not introducing redundant equations, right? So you're not saying beta 1 plus beta 2 is equal to 1, and 2 beta 1 plus 2 beta 2 is equal to 2, which is exactly the same thing, right? So you're not doing that. Every single row of R is a different restriction. So we're going to assume that the rows of R are linearly independent. So the continuous mapping theorem implies that we have this result. And so we have that square root n R beta hat minus R beta converging distribution to a normal with mean 0 and variance RB R prime as n goes to infinity. And since B is assumed to be non-singular, this RB R prime is also non-singular. See, this is very easy. Take A that is not 0 as a vector, okay? And then you have A prime R B R prime A. You want this to be positive, okay? Well, but if you let B be A prime, or if you want R prime A, well, this guy is non-zero because the columns, we just said that the rows of R are linearly independent and A is different than 0. So by definition of the linear independence, this is non-zero. And so now if we just make this B prime, B and B, this is positive because B is non-zero and B is non-singular. So short story, we have B non-singular, R has linear independent rows. So this guy here is invertible. Okay, so we can, do things that involve that in the denominator or an inverse of that object. And that's actually what we're going to do. So, from our asymptotic normality result, we can use the results that we know about, normals and chi-squares. And so we have that n times r beta hat minus r beta prime the asymptotic variance inverse, which we know is invertible, at least with high probability because this is estimated. But then r beta hat minus r beta conversion distribution to a chi-square, which has p degrees of freedom, where p is the dimension of the rows of r, okay, which is the number of restrictions that we have. And so a natural test statistic in this case would be the wall test statistic, which is quadratic form. Okay, is this object that we can say something about uh, its distribution under the null hypothesis. Okay, remember, I want to repeat this because I saw some weird statements last year. So um, remember, C here is a guess value that we say. Suppose we want to test R beta is equal to 17. So C is going to be 17. There's nothing that says that these Tn over here, conversion distribution to a chi-square, when you plug in a number 17. That couldn't be possible because if you, instead of testing 17, you want to test 21, well, then that, which one is going to chi-square, the 17 or the 21? You're changing the values. So we can say, however, that this is going to work under the null when C is equal to R beta, because then we're going to replace this C with R beta, and then we can use the result at the top. That's why we always write under the null hypothesis, which means when C is actually equal to R beta, and then we can use the result that we have, which is this one here at the top. Given this, the suitable choice of critical value is the 1 minus alpha quantile of a chi-square distribution with degrees of freedom p. I'm going to denote that guy as CP 1 minus alpha. 1 minus alpha quantile of a chi-square distribution degrees of freedom p. And the test rejects the null hypothesis when the test statistic is greater than this critical value. That's exactly what we defined before as our families of test statistics. And by duality, as before, we have that we can construct a confidence region for beta, okay, if we just set R equal to the identity matrix, okay. And then what is the confidence interval? It's going to be all vectors of dimension k plus 1, okay, such that our test statistic, which in this case doesn't have R because we set R equal to the identity, is n beta hat minus C, the inverse beta hat minus C, is less than the ck plus 1, 1 minus alpha critical value of a chi-square. And then this confidence region is going to satisfy the requirement that we want. Now, as opposed to the previous one that we saw for the case of the t-test, this one, suppose that you have 20 x's, okay? So this dimension 21. Well, exploring a 21-dimensional space is difficult. Again, could be done depending on the setting, but it's computationally difficult. Not only that, once you have a 21-dimensional ellipsoid confidence set for this, it's really hard to report. So you cannot plot it, you cannot put it in a table. Okay, so again, as I said, in more advanced topics, you need these objects anyway. But that's why in practice people will never do this. They will just do confidence intervals for each individual component without taking into account their correlation and things like that. And the reason to do that is because that's easy to report, that's easy to plot. Whereas this object over here, unless you're in dimension 2, in which case you can plot an ellipsoid, okay, the minute that you're beyond 2, it's an object difficult to compute and difficult to report, okay? Conceptually, has exactly the same intuition as the one that we described before. Now, what about nonlinear restrictions? And with this, I'm going to conclude this kind of review. Well, in that case, suppose you want to test the hypothesis that f of beta is equal to 0. Here, f is just possibly a nonlinear function versus the alternative hypothesis that f of beta is not equal to 0. And then here, f is a function that maps rk plus 1 to rp. Okay, so we're keeping the same notation as before, that p is the number of restrictions that we want to impose. Then we're going to assume that f is continuously differentiable at beta, and we're going to denote the derivative by d beta f of beta. Okay, And this derivative is a matrix of dimension p k plus 1. See, it's funny enough, it's exactly the same dimension as the matrix R that we had before, okay? But in this case, it's the matrix of partial derivatives of f evaluated at beta. So then we're going to assume that the rows of this are linearly independent, okay? Yes, this is like same as R before. Because when the function is linear, R prime beta, well, the derivative is R. So just making the connection that these assumptions just mimic the same assumptions that we had before with R, where R was the derivative. Well, in the nonlinear case, it's just going to be some other object, but conceptually, it's exactly the same. And then we're going to have that the delta method will give us that square root n f beta hat minus f of beta, converging distribution to a normal, which means 0, and variance, that is like the derivative b derivative prime, okay? Which again is exactly the same that we had before with R. Now we have this derivative. And the continuous mapping theorem guarantees that since we're assuming this continuously differentiable, the continuous function, so we have derivative b hat derivative evaluated at beta hat, converging distribution to the object that appears here. So we have indeed a consistent estimator of the asymptotic variance in this case. Once you have that, is you have a statement about beta hat and an estimator of the asymptotic variance, do a quadratic form, a wall test, and you're good to go. Everything that was said in the previous slide applies to this slide here as well. And you can do testing, and you can do confidence intervals. So, as I said, it becomes repetitive. Once you understand how constructing tests like this works, it becomes really repetitive because conceptually they're all the same. When you focus on this class of test functions that reject whenever a test statistic is greater than a critical value. Okay. So that's about that with the review of testing. Any questions about that? All right, let's move on to the next topic, which is linear regression when x expected value of xu is not 0. We're gonna consider the same setting we considered before. I told you that you were gonna get tired of looking at this over and over, where we're gonna be using this through the year or the quarter at least. Let's yxu be a random vector. Again, y and u scalar, x vector. X includes a constant term, x0. Beta is dimension k plus 1 as well, and includes a constant term. And we can write the model like y equals x beta plus u. Now, as opposed to what we have been doing up until now, we are going to assume, or we are not going to assume, that the expected value of xu is 0, okay? And so we're going to introduce this terminology that I assume you're familiar with, that any xj such that the expected value of xj u is 0 is said to be exogenous, and any xj such that the expected value of xju is not 0 is said to be endogenous. Okay, we're going to always normalize beta 0 to view x0 as exogenous, which means we're always assuming the expected value of u is 0. Okay, so I wrote here, note that it must be the case that we're interpreting this regression as a causal model. And then, most of you responded correctly, but let's review that just in case. In the first interpretation, okay, where we assumed that the expected value of y given x was x prime beta, then as a result, we have that the expected value of u given x was 0. And as a consequence of this, we had that the expected value of xu was 0. So if you're interpreting beta as the in a situation where you assume that the conditional mean of y given x is linear and beta is the slope parameter of that conditional expectation, then by construction, you have that this is the case. So in that interpretation, you cannot be talking about endogeneity. Again, it's descriptive. We talk about that. And where you're talking about descriptions, there's no room to talk about endogeneity. In the second interpretation, beta was the best linear predictor, okay? Or, you know, um, x prime beta was a best linear approximation to the conditional expectation. Well, here we show that expected value of xu was 0 by construction. So in this second interpretation, we also saw that if you just want to project y on x's, just to get a prediction for y, or just to get an approximation, a linear approximation to the conditional expectation, then in that case, the error term defined as y minus this best linear approximation is orthogonal to x by construction. So again, this is a descriptive representation, and endogeneity doesn't make any sense there. So now, since there are three interpretations, the one that makes sense is the third one, because here we wrote y equals x beta plus u, and then remember that we view this as a model producing the y's, and this part is what we observe, and this part over here is like factors we do not get to observe. So here, expected value of xu equal to 0 is an assumption between what we observe and what we don't. So here makes sense to talk about endogeneity. Could be the things that we observe are related to the things that we do not observe. And now endogeneity may be an issue. Whereas it doesn't have any room for the first two interpretations that we discussed. So hopefully that's clear. If it's not, you let me know. Okay. So what happens in this case with the least squares estimator? Well, this is something that is going to be useful in the next slides. So the OLS estimand is expected value of x prime inverse expected value of x y. What is an estimand? If you haven't been exposed to that word, it's going to be useful as you move into certain type of topics. Is the parameter that an estimator estimates. Okay, so estimates may be useful in some cases, may be useless in some other cases, but it's a word they use if you want to do it mathematically as a probability limit of an estimator. You give me an estimator, it doesn't matter what it is. Just think about some formula. You sum this, divide by that, and multiply by that. That's your estimator. Then I can ask, okay, where is that? What is that estimating? Well, there's a population object that is converging to. That would be the estimate. Okay, and the estimate of the least squares estimator is this object that we described before. So, in other words, beta hat n converges in probability to the estimate. Now, what we can do is replace y now by x prime beta plus u. And then we have if we work out the second expectation, we have this expression. And so, whereas before we would assume that the expected value of xu was 0, this term would disappear, and then that was our proof that beta hat was consistent for beta. Now, when there's a endogeneity, this term is not 0. And so you have that beta hat is consistent for all this thing. So it's inconsistent for beta, and it has a deviation from beta that we sort of like know how it looks like. Is this expected value of xx prime times the expected value of xu. In the scalar case, where k is equal to 1, we have that beta hat 1n converges in probability to beta 1 plus covariance between x and u divided by the variance of x. Okay, you can say x1 here, which is the same, just that in the scalar case. And the other one is the generic version. So anyway, this is something that you already knew, but now we're just writing here clearly using our notation that whenever this assumption that the expected value of xu is not 0, okay, when expected value of xu equal to 0 doesn't hold, then least square is no longer consistent for beta. It has this extra term over here. So the question is, where is this coming from? What are the usual stories for endogeneity? And so what I'm going to do next is to go over the 3 most classical ways to be concerned about endogeneity. And these 3 ways are still relevant today, and is a way to think about endogeneity. They're not exhaustive in the sense that there could be others, okay? But I'm going to go through them anyway, because as I said, these are like quote unquote classics, all right? The first one is called omitted variables. Suppose here that k is equal to 2. So you can write the model like here at the top, y, beta naught, beta 1, x1, beta 2, x2, and u. And then we interpret this regression as a causal model, of course. And we're willing to assume that the expected value of xu is 0. Okay, so we have this model that says y is related to x1 and x2, and then anything else just sort of like irrelevant. So you can assume that the expected value of xu is 0. So in other words, we have this. The expected value of u is 0, which is always a normalization. Expected value of x1, u is 0. Expected value of x2 is 0. Now, the problem here is that x2 is unobserved. Just observe y and x1. Okay? And then I wrote here, usual simple example of this is when y is, say, wages, x1 is education, and x2 is ability, skills. And we don't get to observe that. So, but we have this belief that if we were able to observe education and skills, that's all we needed, to make statements about wages. Anything else would be irrelevant and uncorrelated with these 2 things. So what I want to do now is to rewrite this model in a convenient way so that we can analyze it. Okay, and let me do this. I'm going to write y equals beta naught plus beta 1 x1 plus beta 2 x2 plus u. And what I'll do next is I'm going to add and subtract the expected value of beta 2 x2. So I'm going to add it first, beta 2 times the expected value of x2. I have beta 1 x1. I have u. And then let me subtract now the expected value of beta 2 times expected value of x2. So now, in this case, I can call this guy over here beta 0 star. Let me call this beta 1 star. And let me call all this u star. So I can write this model of y equals beta 0 star plus beta 1 star x1 plus u star, where we normalize things so that the expected value of u star is 0. So what I did was I rewrote the equation that we had so that we can see what is exactly that we would be doing if we only have information of y and x1, and if we just run a regression of y on x1. Well, the things that we see here is that beta 1, the coefficient multiplying x1, doesn't change. That seems to be good news. The constant term is just going to be different because, that's the normalization that we will need to um, account for the stuff that we don't get to observe. Unless, of course, the expected value of x2 is 0, in which case it wouldn't happen. But then we have a different error term, right? Before it was u, now it's u plus, this this factor that captures what we do not observe, okay? So we can write it like this. Okay, so this is what we just did, okay? Is here repeated, model I just wrote, and then we have this over here. So now, let beta 1 and hat be the least square estimator of beta 1 star in a regression of y on x1 and a constant. So by the formula that we had before, we have that beta 1 at n converges in probability to beta 1 plus the covariance between x1 and u star divided by the variance of x1. But now, covariance between x1 and u star is the covariance between x1 and u plus beta 2, x2 minus x2. This is equal to beta 2, the covariance between x1 and x2. Because again, remember that u is uncorrelated with x1 and x2. So when we compute the covariance between x1 and u here, that'll be 0. So we only remain in the covariance between this and this. So that's what's going on. And if we take that back to the expression that we had here, we have that this is equal to beta 1 plus beta 2 times the covariance of x1, x2 divided by the variance of x1. I'm going to say here the term beta 2 covariance x1, x2 divided by the variance of x1 is called omitted variable Oopsie. Omitted variable bias. So we learned from this simple derivation is that when is omitted variable bias going to be a problem in this specific example, where it's going to be a problem for this to be a problem, if you want, you need two things. First, you need this guy to be different than 0. So in other words, you need x2 to affect the outcome. Okay, you need skills to actually affect outcomes. That would be the first thing. And the second thing, you need the covariance between skills and education in our case is not 0. Okay, so because if these factors are independent, then immediately we have also the condition that we need in this short regression or smaller model. Okay, but in general, when beta 2 is not 0, so the variables that we don't get to observe actually do affect outcomes, and 2, the variables that we get to observe are correlated with the variables that we do not get to observe, we have this endogeneity problem, and we have the so-called omitted variable bias. Questions about this example? All right. Second example that we're going to talk about is the so-called measurement error. Here, we're just going to consider the usual setting. I'm only going to partition x into x0 and x1, where x0 is going to be just the constant thing, the one that is all equal to 1, and x1 are going to be all the slope variables, okay? So you can write it like this. So x1 here is, I'm not assuming that it's scalar. We may assume this later if it simplifies things, but you don't have to. So then y is a constant plus all the variables plus u. We're interpreting this regression as a causal model, and we are willing to assume that x is exogenous, okay? So, but the problem is that x1 is not observed, okay? What we observe instead is x hat 1, which is a noisy measurement of x1, okay? And this is typically called measurement error. Now, today I'm going to focus on the so-called classical measurement error that has essentially three conditions. It says the measurement error has mean 0, which again you can view as a normalization, doesn't really matter. The second is that the covariance between what you're trying to measure and your measurement error is 0. I mean, you can even think about independence. So you can see this as somebody who's typing information in a computer, makes random mistakes, and the errors are not. If, for example, this is income, the errors that you may make to measure incomes could be different for really high income people than for really low income people. Well, you're not saying that. You're ruling that out. You're saying this is uncorrelated, and you can say independent of what you're trying to measure. And then the last one is a measurement error. B here is uncorrelated with the error term in the regression. That is all the factors that you don't get to observe in your regression, in your model. So we're going to rewrite this model again. So let's do it. And again, why do I rewrite the model? I want to rewrite the model so that I can capture what I'm going to be doing, which is running a regression of y on x hat 1. So let's do it. All right, so I'm going to write this beta 0 plus, I'm going to replace x1, and x1 is just x hat 1 minus b prime beta 1 plus u. So I'm going to keep going. This is beta 0 plus x1 hat prime beta 1 plus u minus b prime beta 1. Now I'm going to call this beta 0 star, beta 1 star, and u star. where notice here I don't need to renormalize anything because expected value of u star is 0 by our assumptions. Then if we just look then at our regression of y on the mismeasure x, well, we see here that the constant term doesn't change, the slope parameter doesn't change, but we have definitely a different error term. Okay? By running a regression of y on x hat 1, we don't have the same error term that we would if we were running a regression of y on x1. Okay? That would be great because, we have exogeneity here. So, but the problem is that we don't have that. So we need to run this regression instead. So what happens? Here's what I wrote before rewritten. Again, as we did before, I'm going to say let beta hat 1n be the least squares estimator of beta 1 star in a regression of y on x hat 1. Then beta hat 1n will converge in probability to beta 1 plus expected value of x hat 1, x hat 1 prime, inverse expected value x hat 1 u star. So note expected value of x hat 1 u star is equal to the expected value, and let me replace things for what they are. Remember, x hat is x1 plus b. So I'm going to write x1 plus b. And remember, u star is this object over here, u minus b prime beta 1. And then this has a number of terms. First one is x1 u. Then we have b u. Then we have x1 b prime beta 1. And then we have b prime beta 1. Well, this is 0. This is 0. This is 0. All by the assumptions that we made in the previous slide. This is not 0. So then, if we go back to the equation on top, this is beta 1 minus expected value x hat 1, x hat 1 prime, expected value of b prime beta 1. So, interestingly, in the scalar case, where k is equal to 1, we then have that beta 1 at n converges in probability to beta 1 minus beta 1 times the variance of b divided by the variance of x hat 1. You can write this as beta 1 times 1 minus the variance of b divided by variance of x hat 1. And this is strictly less than beta 1. It'll be beta 1 if the variance of b is 0, which in other words is saying that you don't have measurement error. Okay, you're not introducing any error. The variance of B is 0, then you obtain beta 1. We're fine, it's consistent. And it would be 0 if the variance of B is equal to the variance of X hat 1, which essentially saying you're having pure noise. Okay, what you observe is just noise. And this is called oftentimes attenuation bias. Okay, because it's saying that you sort of like have a sense of what's the effect of measurement error, which is giving you values that are like smaller than what they should be due to the noise that you're in. And this is another case that illustrates, as I said, a classical problem of endogeneity. There's a reason why this is called classical measurement error. There are all these assumptions, okay, that as you can imagine, in many settings that are not going to hold. There are cases in which you're going to have measurement error due to like other things. And whenever the measurement error is more complicated or non-classical, the consequences could be different. But we're not going to focus on that now. Questions about this? All right, so we get to the end. We're going to talk about simultaneity. Classical example is supply and demand. Okay, so we're going to know by QS the quantity supplied and QD the quantity demanded as a function of a non-market clearing price P tilde. Okay, so you write equation. These models here for simplicity are linear. So the quantity demanded just a linear function of hypothetical price, and there are some unobserved factors that we don't know what they are. And then we have the quantity supply, again a linear function of a hypothetical price, and then other stuff that we don't get to observe. And then we are going to assume that these are terms are mean 0 and they're unrelated. Let's call it the demand shock is uncorrelated with the supply shock. Okay, so what we observe is Q and P, the data, but where Q and P are such that the market clears, right? So we always observe quantities and prices that arise in equilibrium. And so what this means is that the quantity supplied equals the quantity demanded. And if we just write that, what we have is beta 0D plus beta 1D P plus UD equals beta 0S plus beta 1S E plus US. The market clearing price sets these two quantities the same. And then, if we just solve, we're going to have the following. Beta 0S minus beta 0D plus US minus UD divided by beta 1D beta 1S. So here we have the equilibrium price. And then note, I'm going to say the expected value of P times, say, US, which appears to be simpler. There's going to be the variance of US divided by beta 1D minus beta 1S. And the expected value of PUD is going to be minus the variance of UD divided by beta 1D minus beta 1S. So what these two things mean then is that P is endogenous in both regressions of Q on P interpreted as demand or supply equations. You run regressions of quantity and prices, Well, doesn't matter whether you interpret that as a demand equation, a supply equation. E is gonna be endogenous by construction, by the feature that um, this arises in equilibrium by setting quantity demanded equal to the quantity supplied. And this is another case where endogeneity usually arises. So, anytime you see prices in statements, you'll see people viewing prices as endogenous. Okay. And you will have to do something about it. So, these three cases: omitted variable bias or omitted variables, measurement error that leads to this attenuation that we saw, and simultaneity, where you have objects that are determined in equilibrium, broadly defined, are three very standard popular cases where endogeneity arises, and people are know this, of course, and so are cases where you that motivate thinking about endogeneity in the first place. So, are there any questions about this last example on simultaneity? All right, this takes us to the end of today's class. Next class, we're going to talk about how to deal with this endogeneity problem, and we're going to bring the usual suspects, the instrumental variables, and see how we can exploit that to still get a consistent estimator of the objects that we care about. And that will be next week.